7, 6, 4, 3, 2, 1, and liftoff. Go.
That was brilliant. That was great timing. Hi. I'm the person who pissed off a turf yesterday. There you go. that was awesome fun. In the end, there were 12 of us who got blocked. Yeah, it was really good. There, what? Only for you. Okay. Why not? Why aren't we getting? Okay, I know what's going on. I'm sorry to all the chat. Yeah. Yeah, there's always something you miss, isn't there? Let's give that a go. Try now, Mary. No, you're not. Okay. No, neither of you are working for. So, hang on. I'm probably not working. I just realized that. Okay, am I now working? Yet? Okay, I was editing the wrong one. That was probably why. Try that. No, no, they can't. Try the other one. Try that one. Nope. Maybe that one. Yes.
Okay. Yeah, all right. Okay.
Now we're working.
Now
I'm terribly sorry, everybody. That's entirely my fault. I had to change my voice meter settings the other day to stop some feedback in another stream, and it messed everything up.
I told you.
Murphy's
All right.
Law.
Murphy's Law.
I apologize, everyone. Try again. We'll go from the top there, Mary.
Try it. Okay. So, hi everybody, and welcome to Scinosium Part 4. So this is the Chronicles of Scinosium. Yay, we'll have audio. It's always going to be an issue, OBS, because it's OBS.
It shouldn't have been an issue. I can actually see if this works before the show, and I didn't look.
I told you to. I told you.
You
did I not say?
You did. You actually did.
Anyway, so my name is Meredith, as you probably know. If you don't, still Meredith. Welcome to Scinosium Part 4. I have my always ever lovely co-host Jen Corner. So Jen, who are you? Where are you? How are you? Why are you? What are you? Etc.
Yeah, that's a lovely way to say that. Well, I'm Jen from Jen's Little Corner, as Mary said. I do science and LGBTQ and all other sorts of weird content, including being naked a few times. Yeah, the look on your face when I said that, Mary. You were not expecting that video.
That was scarring. That was genuinely scarring. I saw way too much of you.
8,500 people have now.
Fuck me.
It is my most watched video.
Why does that not surprise me?
It doesn't surprise me either, but hey.
For me,
The best part about it is it's my most watched video, but most of them have only watched the first 2 minutes.
Yeah, that was me. Okay, and again, a big welcome to Matthew, who is also almost a doctor. Say that 10 times. So Matthew, who are you, where are you, why are you, how are you, what are you, etc.
All right, so to start from the top, well, thanks, and thank you for having me on the show. I'm almost a doctor. As the title suggests, I'm a PhD student, so I'm attempting to try and get a doctorate. So my area of research is in physics. I get to play with lasers on a daily basis, which is something that not a lot of people get to say. Sorry?
You lucky bastard.
I love my lasers. Normally, though, this year I'm more using the lasers as a tool. We can get into exactly what I'm doing a bit later. So I have a background in science. So I have a Bachelor in Science as well as a Bachelor of Commerce, but I'm happy to forget about that if everyone else is. And I have honours in physical chemistry. So I like my science. I've just started a YouTube channel. It was kind of a lockdown thought, and now I'm trying to get it going. So my YouTube channel is called Almost a Doctor. And I go from there. I like telling people about science. I think it's interesting. And I bore my family a lot with it. So now I'm trying to find people on the internet to bore with science as well.
Science is fun.
Science.
Of course it is.
Science is the best.
The process can be a little boring, but when they do find things, it is incredibly interesting. And it's incredibly useful. So there's not a lot of careers, I think, where you can actually focus on your interest and you know that in the long run, even after you've finished, you can still potentially make a massive difference. Even a little difference that someone else builds on.
Even after you're gone. I mean, there are people that, things that were discovered by Galileo or Newton and that are still being used today. So and so it doesn't necessarily have to be the biggest, most earth-changing thing either. Just something little. It could be something that we go back to, we talk about.
Gravitational waves, for example. Was it almost, was it 100 years almost or something after
special relativity, I think, was it was during the 1910s. It was very close to World War One, if not during World War One. And then general relativity was 10 years later. So we're talking, 1920s, mid to late 20s.
I think the prediction of gravitational waves wasn't until the 30s. But that's still that's still 85 years or something between the prediction to the first detection. So
and then
that's just amazing.
And I'm actually about to make a video on these devices called optical tweezers, where maybe they'll be able to be used to detect, as a benchtop detector. So the current LIGO detector has 4 kilometer long arms, and one of the applications of this new one is to take this 4 kilometers by 4 kilometers setup and be able to do the same thing but fit it on a benchtop like what's behind me. Maybe a bit bigger than that, but
nice.
So if you want to hear about that, I'm happy to add.
Please. Let's start with that.
So this is going to be my next video, so I'll try and keep it a little bit cryptic so people can actually follow the channel for that. But essentially...
Can I ask something very quickly? Can you please define what a laser is? Because some people who I am not mentioning myself might not actually understand what a laser is. I know it's a beam of light, but that's about as much as it is. I'm sorry, I'm a complete moron when it comes to things like physics.
No, that's all right. Physics is hard,
she
and
has
it's hard for a reason. It's not, physics is not generally intuitive. You only need to look at Richard Feynman's quote of anyone who thinks they've understood quantum mechanics really has not understood quantum mechanics. There is a bit of quantum in lasers, but the main part of a laser is it's a device that produces a monochromatic, coherent beam of light. So I'll break that down. So monochromatic, mono meaning one, chroma refers to color, or in this case, wavelength. So it means one wavelength. The lasers produce one or as close to one wavelength as you can get. There's always a slight bit of lead on either side. And the coherent refers to the actual waves. So we can think of sound waves. You have your peaks and your troughs, and if you can cancel them out, or you can build them together. And of course, they add together. When you're dealing with a laser, all those peaks and troughs, so if you have the waves kind of going up and down, the next one, they're all in alignment. So the peaks all line up, the troughs all line up. It's really, really useful for research, but you probably won't see it with your own eyes. I have a video on my channel about what lasers are and how movies get them wrong. I go through that, and I even got photos of lasers there if anyone wants to have a look. So that's basically what a laser is, exactly how you make them start to get more complicated. But they are very, very fancy devices that produce a relatively simple but incredibly useful output. Hopefully that covers that a bit. And yeah, the things you can do with lasers is incredible. There's so many different uses, and I have fortunate enough that I get to play with one or two of those uses here and there. So yeah.
And interrupting again because I am a bitch. I just want to say I apologize for that. I just want to say thank you to everyone in the chat that's come in. So I am seeing Critical Cripple, Junk Shop Library, Video Pirate is yelling at me. Again, if you expect my streams to start on time, you are wrong, but only in a loving way. Mark Caesar is also talking about me chasing my snake.
Is not actually there?
I think Mark's still in there.
Jen's
little corner. Oh, Notcha. No, he's working. Jen's little
you missed
corner.
the joke.
So yeah, Jen's little corner, thanks for coming. Almost a Doctor, thank you for coming as well. I appreciate that. Godless Sewing, thank you for coming, and Fly for Mill. And I think Ricardo Oliveira, I can never pronounce your name. I'm sorry, Ricardo. Amiga Nuts. So thank you everyone for coming. And
Ricardo Oliveira.
Oliveira. If someone says the name before me, I can say it, but off. Oh, Wolf. Hello. I might add you as a moderator. Wolf the Red's here. And
I've only got top chat and not live chat on. That would explain that.
Okay, sorry about that, Matthew. So
all good.
Continue.
So welcome everyone in.
Yeah.
So yeah.
It's always nice.
There's my hello as well to everyone in the chat and everyone watching. So okay, so I was talking about the optical tweezers. Of all the experiments I've got to do, particularly when I was undergrad and I was forced to do experiments within a few hours, which when you actually get into research, science does not take a few hours. It takes a lot longer than that. One of my favorite ones, although at the time was incredibly stressful to get working, was the optical tweezers. So what is an optical tweezer? It's essentially a tractor beam using a laser. So if you think tractor beams are something out of science fiction, no, we can actually make them work, just not quite yet on the scale that you might see in a movie where a spaceship comes over and steals some cows. I'm not sure why they seem to be stealing cows or taking the occasional human, but I don't know. To each his own with their imagination. So what essentially you do is you can focus a laser beam, because laser beams don't necessarily travel in a straight line. You can actually focus them with lenses, and they will actually diverge after a while. So what you do is you focus it down, and where that focal point is, it turns out that there's some amazing physics that means that if you have a small object there and you try to move that object out of that focal point, then the light itself pushes the particle back towards that center point. So you can actually hold small particles and suspend them using a laser. I've actually done that myself. You can actually trap them even in solution and move them around. You can watch objects fall in. And the current state, they actually do this in a vacuum. It's called Optical Levitation, which I think is quite cool. And it is exactly how it sounds. You can hover objects in a vacuum. So like in space, against the forces of gravity, just using a laser beam and various different types of particles. And you're thinking, okay, that's cool, but what can you do with it? Well, the original kind of inventor of this, or one of the original founders of the field, was a guy called Arthur Ashkin, who won the 2018 Nobel Prize. He was the oldest guy to ever win a Nobel Prize. I think he was 96 when he was awarded the prize. I'll have all this in an upcoming video. And one of the things they did with it, or he did with it once they had it, was they trapped biological particles. So you get your laser, and then you can hold things like bacteria, viruses. They actually have a video in the Nobel Prize lecture on it, where they actually show him trapping what I think is actually a sperm cell. So you can actually hold these biological particles, so you can study them. You can do forces without actually damaging the particles. And that was the original one. But as I indicated earlier, you can use these for detecting gravitational waves. So you can get force detection. And to give an idea of how sensitive these things are, if you're holding a phone in front of your face to send a text message, there is a gravitational force between your body and the phone. It's tiny. Gravity's weak. But this thing is about 1,000 times more sensitive than those. And this is a few years ago, the papers I was finding on that. So this is a detector that can measure the gravitational attraction between you and your phone. So these things are pretty cool. You can do a lot with them. And I am really looking forward to the day where we have all these things on your average benchtop in a lab. Oh, maybe that's a bit my own imagination, that last one.
So when are we going to start kidnapping cows?
That's going to be a little longer yet. I think we're going to need a bit more power to pick up a cow. But there are other ways of making the beams so you can lift things up. But they're a little more science fiction-y at this stage. But theoretically, still possible.
Surely one of the problems with a bit more power would be the fact that then you would get to the point of starting to damage what you're trying to lift.
Yes, that is also a problem. And the world's most powerful, the world's largest laser is at the National Ignition Facility. It's the American fusion reactor. That laser is so powerful that if you made it any more powerful, it will ionize the atmosphere, which means it will start ripping electrons away from the atoms in the atmosphere. It's so powerful that it starts to destroy the air. Yeah. So you actually get to a point where the laser cannot get more powerful. I don't think you'd quite need that power, but it depends what you're lifting. So, yeah. Lasers can be all sorts, from a little laser pointer to something that will destroy the air.
Yeah.
That's pretty impressive. So hopefully not the entire atmosphere, just that localized area of atmosphere.
Yeah. I think by the amount of power you'd need to destroy the entire atmosphere, you're probably better off just building a giant, hydrogen bomb or something like that. There's more efficient ways to destroy the Earth than a giant laser. So.
Yeah, the amount of energy required to strip the electrons from all the atoms in the atmosphere would actually burn the planet.
Yeah, so we may as well
just blow the planet up at that point.
Yeah, exactly. But let's not give the evil geniuses in their lairs any more ideas.
It is one of the problems with the ideas of lasers as weapons in space and things like that, is that the amount of energy required to make a laser that's powerful enough to do significant amount of damage in a fast rate of time is a lot. It's so large that the power source you'd need for it, you might as well just have a bomb in the first place. The bomb is more efficient.
Actually very interesting on that. So I know I sound like I'm plugging every single one of my videos, but my second video is on Project Excalibur, where they tried to do exactly what Jen is kind of saying, where they were thinking, okay, let's try and build a giant X-ray laser. And there's a couple of reasons why X-ray lasers are harder to make than your regular laser. They get really, really difficult. You need a lot more power per photon. Plus, X-rays are also hard to make laser cavities, so you get less time to actually build the beam. So I think somebody must have just in a meeting been like, what's the most powerful thing that we can think of? And someone went, a nuke. Can we try a nuke? And instead of everyone taking that sarcastically like it was meant to, somebody took it seriously. And that's exactly what America tried to do, where they tried to build a space-based X-ray laser that was powered by the detonation of a nuke. Surprise, surprise, it didn't end up working very well. And of course, nukes are banned in space, but America kind of ignored that for a little while. It turns out that, yes, you are much better off just to detonate the nuke in space. You get a giant EMP pulse that comes out of it. So when America first detonated a nuke in space, they didn't know what was going to happen, or they didn't really know what was going to happen. They ended up taking out a number of their own satellites and then shorting out the electrical grid in Hawaii. And then they were like, oh, this is not good. Let's not let anyone have nukes in space. And the Russians agreed. So that was back during the Cold War. So it's very fascinating. But yes, that was probably the biggest laser anyone's tried to make, or the most powerful one using any kind of bomb. Yeah, but there were problems with actually focusing the thing. So at least we don't have to worry about them targeting any of us with it.
And of course, you've got the problems of you run up against the laws of thermodynamics anyway, which is why it's more efficient to launch the bomb in the first place and try and get the energy out of it and turn it into a laser.
It was meant to be a defense weapon, but yeah, it's weird to think that a nuclear bomb was meant to be for defense.
Yeah. Well, it wasn't mutually assured destruction.
Yeah. In this case, it was to take out the incoming nukes.
Yeah.
So to make the other nukes obsolete.
SDI.
Yes.
SDI. So strategic.
Yes, SDI. Yeah.
It's Strategic Defense Initiative. Star Wars.
Yeah. So you ever thought nukes and Star Wars went together? It does sound like the Death Star, but the Americans tried it.
Now, talking the Death Star, isn't the Death Star a totally impractical weapon?
Yes. It also doesn't work like that.
No, lasers don't work like that.
Yeah, no, this is what my first video was this kind of like how bad lasers are in like kind of movies. And yeah, that's not a practical weapon. It just at all. Also, it doesn't do what lasers do. So even if it was real, it's not a laser as such. Lasers don't blow things up unless you're firing the laser at explosives. Then the explosive goes off.
You could heat the planet up, perhaps. You'd burn the atmosphere first. But it's a totally impractical weapon anyway. The amount of energy... I mean, basically, you'd have to have a small star inside that Death Star to get enough energy to vaporize a planet. And and you don't even need to vaporize a planet to kill all the people on it.
No.
You just need to vaporize the atmosphere.
You don't even need to do that.
If you had the Death Star, what I would say is probably one of the most effective ways to damage the planet, to release what would be like a giant smoke cloud. So just stop the sun getting in. If you've got a Death Star, I'm sure you can release, there'd be a giant smoke generator. Stop the sun getting in. Well,
yeah, let's create a nuclear winter on the planet. That screws them.
Yeah.
They all have to leave now.
Also, I saw someone had a question in the chat. There's a few of them. Someone's asking, what does laser stand for? Light amplification by the process of stimulated emission of radiation. So, yeah, it's a long one. All it is an acronym for what the thing does. And the original term was maser, because it was done with microwave. So microwave amplification. And then they became known as optical masers, and then became lasers. So you also get Zasers and as well if you're doing X-rays. So yeah, laser. It's stimulated emission is the kind of the physical working of how they operate. It's quite complicated without diagrams, but it's to do with you have to pump and get all of the molecules in your laser very excited so that they give off more light than they're going to absorb. Because if they absorb more light than they give off, well, you won't have a laser beam.
Most of the modern ones are done by exciting a gas to emit the light.
Yeah, in fact, my channel header is a photo of a gas laser that I took up in the senior labs.
You're basically using the emission properties of the gas to create the laser for you.
Yeah, and then you design the cavity to amplify what properties you need.
Which I just realized saying what I said probably explained that to no one. Sorry, Mary.
Yeah, lasers are really cool, but it gets quite complicated very quickly as to how they work. But no, I mean that's physics. It's not meant to make sense.
Never.
I mean,
Never.
but it does. It actually does make sense once you go in and study it. I mean, the one of the few things in physics that's really hard to make sense of is quantum mechanics, because it's not intuitive at all. But a lot of physics is intuitive. But it's not intuitive at our macro level of looking at the world. We have to come down to we have to start getting down to the small scales. And as you get into smaller and smaller in the scales, it becomes less and less intuitive.
Yeah, and I think the same goes probably for the opposite. I don't know if you agree, but when you start to get the massive scales, like astro scales, when you're dealing with, say, black holes and massive gravitational
as soon as you have too much gravity, you go, it doesn't make sense. It doesn't make sense.
Yeah, and I think that's the other end, because our brains, they're simple monkey brains that evolved to survive. Yes, they didn't evolve to survive in or close to black holes.
Although there is a theory that our universe exists in the event horizon of a black hole,
which makes sense. I'm just going to do a little bit more. I'm just going to do a little bit of more housekeeping and stuff. Anyone who has joined in since I last said hello, welcome. I think I didn't see Nerdy Rodent, Atheist Ants, I think Brainbug. Did I say hello to you earlier? Anyway, if you
and Anja.
No, Nacho's still not here. He's still at work. Aunt Jer, sorry. God. Sorry, it's Jen. Okay, so I am, of course, as you know, monetized. So if you want to send any questions, ask any questions, just you can super chat me, or you could PayPal me. I put a link in the description, or in the chat. If you wanted to send it to me through PayPal, I'd prefer that, because it takes forever, and YouTube takes 1/3 of the income through PayPal's, and just at me, or you could just at Andrew and not outsource, not pay for questions, because yeah. But yeah, so if you wanted to financially support me, it would be great. Actually, Andrew, Matthew, do you have a charity or something that you're associated with?
No, unfortunately not yet.
Okay.
Well, there's been a couple of interesting questions in the chat.
There has been. So, at least definitely at one of us. If you've got a question. I'm just saying, if you want to send me super chats or money, that's it's up to you. It's just like, do it. If you want to do it, you can. If you want to do it.
Let's see.
Yeah, I'm looking. There's a lot of really good questions there. There's one that's got my attention. Could I just quickly try and answer the how effective with sharks with laser beams?
Yeah, I saw that.
So anyone who's watched Austin Powers will get that reference. Maybe we can just go for some angry fish instead. No, not effective in the slightest. Sharks are not easy to get to attack humans at all. So making the sharks attack something just because you put it near the shark is difficult enough. If you put a laser on something in the water, if you're thinking the ocean, it's quite cloudy. That laser beam is not going to go very far.
And all the energy dissipates into the water.
Yes. There's a lot of just scatter the light. You're not going to get much. And also the amount of power you'd need to actually kill someone with a laser, it would probably just, the amount of equipment you'd strap to that shark would probably drag the shark to the bottom of the ocean. So if your human is also at the bottom of the ocean, they're not alive either. So yeah, not effective at all, as cool as the idea might sound.
And on top of that, you might turn the shark radioactive and turn it into a kaiju, which just wouldn't be a good thing.
No, let's not zap any more of nature with radiation. And by radiation, I'm referring to the damaging, ionizing radiation. Not just like light rays.
Nerdy Rodent does ask a good question, though. Which would be the best sea creature to attach freaking laser beams to?
I'd have to go with the blue whale just because you can get more batteries on it. You need a lot of power without sinking the creature. So let's just go with the biggest one. Maybe if we can resurrect some ancient creatures, maybe go with a nice Ichthyosaur, like a giant prehistoric creature as well.
A megalodon. If you wanted a shark, a megalodon.
Yeah, I mean, they're scary enough as it is. Even just in skeletal form, they're like, fucking Jesus Christ.
Yeah, now, I know we're not talking about physics here now, but did you read the recent study, the new study they've done on the megalodon, where they were using averages across different types of sharks to get a better estimate for the size of it?
I don't think I've read the paper, but I
didn't read the paper. I read an abstract from it. I didn't actually read the entire paper. But basically, yeah, go on. No.
Oh no, sorry.
You're the guest. Go.
No, I was just going to try and qualify which one because I think they've done a few studies like that. And I'm
talking about the most recent. I can't remember who it was.
I can't remember whether that's the one I heard or not. Sorry, this is not physics.
Yeah, I only read it a couple of weeks ago, and it had only just recently come out, so this is fairly recent. Yeah, but basically their calculations basically showed that Hollywood's overstatement of how big the megalodon was wasn't wrong. They're actually considerably bigger than what we thought they were.
Yeah,
I'm glad I did not evolve a couple of million years ago, frankly.
I wouldn't be gone swimming.
They tended to attack really large creatures, so
because they were large.
Humans okay. But they had a very nasty hunting technique. Their technique, from what we've seen, because they left teeth in the animals they attacked. So we have very good fossil evidence of how they hunted, even though apart from their mouths, we don't really know what they looked like because sharks are made in cartilage. They don't fossilize very well. There's one potential fossil find. I don't think they've actually released any papers on it that might. But their hunting technique was to ram their foes in the hard bony bits and literally crack their ribs or collapse their spine or something and immobilize them. And they didn't do that to whales. Or rip flippers and tails off so they couldn't swim away. It was, they were nasty. You would not want to be attacked by them. But it was probably a combination of reasons why they definitely went extinct. They were shallow water hunters, so kind of where your beaches were. So if they were still around, we'd know. There'd be a couple of humans that went missing. But they were huge.
You did say they were very big, and we wouldn't actually be considered prey by them because that'd be
probably not
living off like salmon, like little fish about that big. It wouldn't be worth eating us. Well, that's good. That's good to know.
Potentially, but then again, we've never seen one, so maybe they'd look at the small thing, be like, that can't fight back.
And all our evidence for them is from jaws and teeth. We have nothing else of them.
Yeah, as I said, there is that one potential fossil find that might have a bit more than the jaws and teeth, but I don't think anything's been released on it.
Yeah,
I would love to read a paper on that if they do. But yeah, that's the thing. They don't even, like, the things where they always show it looking like a great white may not be the case. It may not have actually looked like a great white. Might have had a more stubby, flatter head. All sorts of things. There's some very interesting videos out there on YouTube that go into a lot of depth in those, and I like watching them in my spare time.
Yeah,
like a true nerd.
Of course, but if someone calls me a nerd, I love it.
Yeah. Well, you're in good company here.
I think we all do the same thing. I mean, we all have our fields that we love and that we want that we work in and deal with, but we're all like, that bit of science is fascinating. There's been a couple of times I've seen biology articles and then had to message Mara and said, "What the hell is this about?" Because this looks interesting and I don't know what it means.
I do. Shock of all shocks. Oh my freaking God, this is incredible. This is like a miracle. We have a genuinely serious question. Holy shit. Nathan Jasper does ask, are laser-based fusion reactors the future of energy? How do they work? See, I can ask a serious question. And in my opinion, that's almost as miraculous as lasers themselves. So.
Yeah.
Poor Nathan.
I'll do my best to try and answer that. So the laser are doing, I think, just to refresh anyone who may have joined later, we were talking about the National Ignition Facility earlier, one of the world's most powerful lasers. That's the one that's doing this kind of research. And to say whether it's the future or not, so I'm going to go, so to answer whether it's the future of energy production, if I thought I had psychic powers or the ability to predict the future, I don't think I'd be doing a PhD. One of the problems with fusion is it's very hard to sustain, so you can't run these things for very long. But essentially what they're going to do is, so this is actually some of the same physics behind how the optical tweezers work, but light has no rest mass, but it has momentum. Probably thinking, why is that useful to fusion? But what that means is that momentum is, you can think of as the ability to push things. It's mass times velocity, conservation of momentum. If I punch the mug, it's going to want to move. Now, light, even though it has no rest mass, does, because of E=mc², have some momentum. There is a mass equivalent. So photons, if you get enough of them, can actually push things. So if you have a lot of them, you can do a lot of pushing. So what you do with this is it's actually a very low-powered laser that they just amplify the hell out of to just keep making that beam more and more powerful. Then all that light comes smacking into a very small pellet. It's got your hydrogen in it. Fusing hydrogen is one of the most efficient per atom fusion reactions you can do. It's what the sun does. They're trying to replicate that. And it pushes and compresses that pellet so that the hydrogen atoms get so close together that you make what's essentially a mini sun, and they can fuse. And when they do that, they give off energy. So you have to put a lot of energy in, and then you're hoping that the energy you get back is a bit more. And that's the big problem with fusion reactors, is that sustained reaction to get that energy back. It is a bit energy positive, so a lot of the reactors around the world are starting to get energy out, so not just the fusion ones, the laser fusion ones. But the problem is you generally can't run these things for very long. So if they can get that problem, if they can make it more sustainable, then it could potentially become the future of energy. I really do like the idea of fusion. I hope they get it working, because it will be a very, very clean energy source that produces helium, which is actually a limited resource. So we always think about energy generation as causing waste of some kind. Even the clean ones like solar, you've got to make the solar panels. Eventually they break down. Whereas if you do this, yes, you'd have to keep the facilities running, but you'll be able to produce useful materials, things that we're actually short of. So it's an amazing technology. Exactly whether they get it working or not, anyone.
Yeah, that's why you should never, ever, ever buy helium balloons. Never buy helium balloons, because we are running out of it.
Yeah. There's also another good reason why you shouldn't buy the helium balloons. It's not pure helium. It contains a few of the other noble gases, including the radioactive ones. So yes, occasionally, if you've ever breathed in a helium balloon for a squeaky voice, that's probably not going to do you a lot of damage. But if you're doing it frequently, I wouldn't recommend it. If you want your xenon and your radon in there, well, maybe it won't give you superpowers. That's not how radiation works.
And also, balloons are a massive source of plastic pollution as well. So there's nothing exciting about helium balloons. So please do not do that. Balloons in general aren't that great for the environment anyway.
If you're going to have balloons, at least have ones that don't fly away.
Yeah.
That you will pick up and deal with properly at the end of.
Yes. Actually, what I did find was really interesting is that we mine helium.
Yeah,
I thought that was really interesting. We mine
Yeah.
helium above beta decay, decaying radioactive deposits, which
Yeah.
I thought was really interesting when I found about that. We actually mine a gas.
Yeah,
Thought that
it's-
was an interesting tidbit.
yeah.
Well, there's no
it's-
other way we can get it, is there? Because there are no compounds of helium.
No.
It is.
I think
the
you
most
can
inert
actually do
gas. You can
You
do
can
it.
actually make compounds out of it, but it's hard.
But
And
it
you got
doesn't
to force
happen
it.
in
There's
nature.
nothing naturally occurring.
No,
Which
that we know of.
But yeah, but what I find really, we know of. But what I find really fascinating about helium is it's the second most abundant element in the universe, and we're short of it here on Earth because of physics. If any of it gets into the atmosphere as just loose gas particles, off into space it decides to go.
Yeah.
So bye-bye helium. So if you pop your helium balloon, bye-bye helium. But it used to be, they used to get a little bit of as a byproduct from the early days of nuclear reactors. And when they were doing radiation chambers, there was this one where they used as a detector where it would hit and then form that helium, but it was not, that was very early days and they didn't run that reaction for too long. So they used to make it, but not anymore. And I don't think it'd be the safest way.
Fuser reactors, to create helium as well, but it's cheaper to mine it as well. That's the ones that use the magnetic loops to cause fusion. It's definitely not an energy positive fusion reaction, but you can use it to create helium.
Yes.
So,
which is why if we can make it energy positive, it's even better.
Yeah.
Yeah.
It is the one type of fusion reaction that you can do easily in a lab, which is actually, but it takes an awful lot of energy to create a very small amount of helium. So we can actually make helium in the lab. It's just not economically viable to make helium.
So, what is probably your most coolest discovery around freaking laser beam detached things heads?
In terms of things like scientific discoveries I've made, or just things that I've learned, or
well, both. Have you made a
so
scientific discovery? Oh.
I actually this year I had my first time I was first author on a paper, so I can now say I published a science paper. It's really good, and it was on lasers. So it's a whole new way of relatively new. It's been around, like the idea's been around for a while, but it's kind of just starting to work into building lasers with it. It's called polariton lasing, and it tries to cut out on all the energy requirements. And I found a new way of doing it where you can feed energy into your materials much easier. So to go back to the acronym of lasers, I think would be the easiest way to explain it. So the SER is stimulated emission of radiation. So to get stimulated emission, as we mentioned earlier, you have to excite most of the atoms in your material, whether it's a gas, a solid, there's a laser diode, and that takes a lot of energy per volume. So you need to get most of them excited. Make whatever puns you want with that. But what if you didn't have to do it that way? Because to do that on the electronic level, electrons don't all like being in the same state because quantum mechanics. So to drive them to all be excited is difficult. But if you could work with something that didn't involve electrons or electronic levels in the same way, you could maybe get around that. And that's what polariton lasing does. So it makes a really fancy sounding thing. It takes advantage of Bose-Einstein condensation.
Okay. Yep.
So
I want to talk to you about this. Remind me to ask you about it later.
I'll do my best to remember. So,
I will make notes. How's that sound, Mara?
Yeah. So before I bore too many people in the chat who are not physicists, it's just a really fancy way of trying to get around the energy requirements to make a laser work. So it means that you can power a laser with a much lower energy. And I found a way that you can have a material we found a material that you can absorb a lot of energy into, and then it will feed that energy into a second material that gives you your lasing. And it's been done in other areas. It just hadn't been done in polariton lasing. So it's not a massive breakthrough, but it was really, really cool because it means that you could potentially make lasers for sharks or whales where you didn't need as much battery packs on them. So you could potentially do it with a lot less energy. And that's my one. In terms of what I think is my most fascinating discovery or my favorite thing that I've learned about lasers is probably to do with the optical tweezers as a potential benchtop gravitational wave detector. As a nerdy physicist, hearing those words together when I was in the lecture, about midway through last year, I was like on the edge of my seat. I was like, yeah, let me at it, because that to me is amazing.
Do you want me to give you another nerd orgasm about that? Go and look up.
For it.
Go and look up a desktop particle accelerator. The aim is to use lasers to push the particles around and accelerate them on a desktop particle accelerator, which will be able to get in it. Well, they won't be desktop, but it means you could scale down something like the CERN Super Collider to a room if they get it to work. That is something cool with lasers. So instead of using electromagnetic fields to accelerate, they'll be using lasers to push the particles.
Yes,
nice.
Science where bigger is not necessarily better.
As a general rule, it's not, because it's super freaking energy
expensive as
inefficient.
well. Yeah, it's expensive to run and expensive to build. If you can build it smaller, you make it cheaper and more efficient, and more people can do things. One of the things that excites me about the prospect of shrinking down particle accelerators to where they're a room is then you've got the ability to mass manufacture antimatter. Now, you're talking about wanting fusion. If we can mass manufacture antimatter, we solve a lot of our problems as far as space travel and things like that go. Because you don't have to worry, can you make fusion? You just build the antimatter on Earth and fuel your spaceships with antimatter. We're talking Star Trek here, people. No, it's not quite the same, but an antimatter rocket is one of the most efficient rockets we could build. And we could build it now. We have the science for it. It's the antimatter's the problem.
Yeah, because it tends to go bang.
Yeah, that's the other problem with antimatter. Pen traps are not the most efficient. Are only
safe.
99% efficient in containing antimatter, and that's that little 1% that's the problem.
And if you're on a long space flight, I don't like those odds of that 1% over and over and over.
Yeah, you are eventually going to
years.
Bore a hole in your pen trap somewhere, and antimatter will escape.
But in which case, it doesn't really matter where you are in that spaceship.
No.
Yeah.
There was a question by Nathan Jasper. You did kind of touch on this earlier in the stream, but it's probably just to add on to that question. Why are lasers different colors, and are there any advantages to different wavelengths? Like we've got the reds and the green lasers, and so what advantage would a red and a green one have over ones inside and outside of the visible wavelength?
Okay, that's actually a really, really good question, and that gives me a chance to give a little bit more background as to how they work. So, as Jen mentioned earlier, you have to build. You rely on the optical properties of your material to make the laser. That material is referred to as your gain media. Each laser, you'll find lots of different lasers with different gain materials because you want different optical properties. And when I'm referring to optical properties, I'm talking about if we put energy in, what wavelengths, what colors of light does our material give off? And then what you do is you try and pick your most favored emissions or emission wavelengths, and then you build your cavity to support those ones. So if I change the cavity or I change the gain media, I can change the wavelength. But there is also something else going on there too. The longer the wavelength, the less energy, just from a basic physics point of view, this is not to do with our technology, it's just how the reality of lasers is, the easier, the less energy it takes per photon to make that laser work. So infrared lasers require less energy than, say, an X-ray laser, which is why when I mentioned Project Excalibur and trying to rely on a nuclear blast, that's because X-rays are incredibly energy inefficient to try and get into a laser. It's very, very difficult, whereas infrared's quite easy. So on that, there are kind of uses. Now, in terms of why might, say, a green laser or a red laser have different uses, well, it depends what you want to use it for. So in research, my area of research is actually gas detection. And we need to rely, and we're relying on the fact that at the moment we look at methane. Methane absorbs particular wavelengths of light, and it has one really nice absorption band at about 1550 nanometers. So that's the infrared. So that's the kind of radiation that will heat things up. It's the same wavelength that optical fibers for communication work. So if you're relying on, like the NBN or optical fiber communication in the internet, they're generally going to use that wavelength because it's easy to make those lasers. They're in mass production. So why not? It's already there. So we can use those for our research. So that's one thing. It's a slightly longer wavelength, so easier to make the lasers I've already mentioned. But it also, in my case, that's the wavelength that methane absorbs. So we can use that to get the methane to absorb it, and then we can try and measure how much light goes missing. And then by how much light goes missing, you can detect how much of the gas that's there. I'm happy to go into what my current research is in a bit more.
This is something I was really interested in me when you were talking about it was, how you were using the absorption and emission spectrums in both the lasers and the gas itself that you're detecting to detect how much gas there is. That is just absolutely fascinating.
Yeah. So just to finish off, why you might use different wavelengths, it really depends on the use. So, say we always typically think of laser pointers as being green or red. That's because they're easier to make than blue. You can also blue, violet, and ultraviolet lasers are much harder to make, but you might want to probe something in those regions. The other downside to, say, an infrared or UV, so things that are outside the visible spectrum, is you may not have a blink response to it, which means if the laser goes into your eye, you may not realize it has, so you won't close your eyes to stop the laser beam, so it becomes really dangerous. And they scare everyone with 90s animated videos for safety inductions where they show someone's retina boiling and bursting the back of the eyeball, which is what will happen if the laser beam is powerful enough. So you want to choose your laser very carefully, and you don't want to mess with them. And a little side note, the green laser pointers that you generally can buy overseas really cheaply and somehow get through customs really easily? I don't actually have one, but I've seen a few research groups here. They're reasonably easy to get licenses for, I think. But they might only be low-powered in the green, but they also leak a lot of infrared laser radiation just on how they work, which means that you might think that because they say low power on the side, it's only the green wavelength, and you end up blasting your eyes with a lot of unexpected radiation. So don't ever look at those or don't get yourself in a situation. There was one story I heard from a professor where he had a student who was setting up a experiment in the lab. He was meant to have had at least a few years experience in physics by this point with an infrared laser. And he was using what was known as a class 4 laser, which is the top dangerous class laser. These are the ones that will do the damage I mentioned earlier. So if you see class 4 written on the laser, you want big, thick goggles or going, I'm not going near
And be
that.
really careful with those goggles too, because generally the goggles are manufactured for the wavelength of light that you're using in the lasers. So a set of goggles that were made for one set of experiments may not work for another, because the wavelengths of the lasers are different, and the goggles are designed to block out those wavelengths.
Yes, and you have to. There's all these little numbers, and they're all printed in tiny print on the top, and after a while, you get an idea based on the color of the glass too. What's going through, what isn't. Some of the really thick ones are the more powerful lasers. So the ones that have the higher power, they're so heavy, but you don't want to take them off in case something goes wrong. But on that, this story, the student was setting it up, and he was trying to. So he had the laser going through an optical fiber, because in research they're really useful ways of aiming your lasers, because then you can just point it where you want, pass it through some lenses. It's good if you want to take one from side of the bench to other. But he was putting it on like the table, and he was putting it on a card, he was putting it on his hand, and he couldn't see it. And he somehow forgot that it's infrared. You can't see it anyway. So exactly the same reason or same thing that you don't do with a hose, you never look down it to see why it's not working.
Oh, for goodness
sake,
did it. No.
And the professor telling me said that this guy dropped it, like, because it gave him a shock of pain, and really luckily it didn't do any permanent damage.
Oh.
But it was just like, as a laser physicist,
you do stupid things every once in a while.
Yeah, but lasers are like hoses. Never look down them to see why they're not working.
No.
That's the summary. And
you keep going, because
no, sorry.
Questions. So you okay, sorry. I've got two quick questions. One from Brainbug. I will ask a bit later. But thank you very much for the super chat, Brainbug. But Nathan Jasper asks a good question. I get how matter becomes energy, but when and how does energy become matter? Do we know the answer to that?
That's probably a question for some of my astro friends or high energy physics. Sorry?
That's a question for Dr. Carl.
Yeah, maybe I'll ask him if I see him. His office is actually down there. I'm lucky, yes. He's not there very often, but I occasionally get to pass him, and he's always awesome. If you ask him a question, he always seems to answer it. He's always been very friendly to me. So
I think the point of that question is you're looking at it kind of wrong. From a physics point of view, energy and matter are equivalent. You could think of matter as tightly packed packets of energy. At the quantum level, it's the same thing. When we talk about splitting atoms and you're releasing energy, what you end up with is other compact chunks of energy, which are the new molecules, and the less compact ones are the radiation that escapes. They're still molecules. They're still packets of quanta. They're still either bosons or leptons or whatever, or energy carrying particles. They're still quantum particles. So everything in that sense is the same. From the point of view of physics, matter is condensed energy. That's all it is. So everything actually is energy anyway. So that concept of E equals mc squared is what the energy you get out when you unpack something that's big. So to do it in reverse, basically you have to put enough stuff together in a small space that the interactions between those particles hold them together. So you basically need you need the nuclear forces between the molecules to be strong enough that they overcome the larger forces that want to tear them apart.
Yeah, that's probably a better explanation than I could have given for that. I do want to add one little kind of interesting side note. In the early universe, so we're talking the moments after the Big Bang, and then relatively early, I mean it's 14 billion, nearly a 14 billion year time scale. So early is a relative term, very relative term here. The universe was actually too hot for matter to form. The entire universe was just energy. And then as it cooled down, those packets could form. So there was a point at which there was no such thing as hydrogen, electrons, protons, etc. That all came later. Just to add on to what Jen was saying, I find that really interesting.
If the early universe had been completely flat, so it had been evenly mixed in all the energy, you wouldn't have had matter form.
Yes, no, great, because
the early universe was lumpy, and that is why we have matter. It's why we ended up with galaxies and stars and everything. The Big Bang, the expansion of the Big Bang was lumpy. It wasn't uniform, which is why we're here. If we had a uniform expansion, that wouldn't have happened. So it is an interesting aspect, and we see evidence of that in the cosmic background radiation. We also are seeing it now in the fact that it appears in certain areas of the looking out at certain areas of the universe. The expansion of the universe is not consistent across the entire universe, which is part of that same thing. It's like that's part of what was required for our universe to exist as it was. Because if it had all been uniform, it would have just stayed uniform, and it would have just cooled down evenly over time. But the universe didn't do that.
A bit of chaos is really good.
Yeah,
and
exactly. That chaos.
Yeah, and to add to that energy thing, I always find this just kind of a little mind-blowing as a thought experiment. Because energy and matter have an equivalence. If I take an object, I've got my mug at hand here, my nice little periodic table of mug. If I heat this mug up, it weighs more. Not detectably to any of the scales we've got, but just because of that, I can make something weigh more because it's hotter.
Yeah,
that's cool.
I just
brain bugs.
Oh, sorry. It's the same with when we think of solid matter as being solid matter. It's not. No. The thing that stops you falling through your seat when you're sitting down watching it is the electromagnetic force between the particles. It is not the particles themselves. The particles are tiny and they all move past each other. It is the electromagnetic force that's there that stops you moving through other things.
Brain Bugs, question is, what is your favorite dinosaur?
Ooh, that's a hard one. This is going to be nerdy. Now, with that, does that mean that it has to be in the Dinosauria clade, or could it be like just a prehistoric animal?
Let's go prehistoric animal.
Let's go prehistoric.
I'm not sure I helped myself on that one. I just opened up for more creatures.
We're evil.
It depends on probably the time period. I've got a couple that I really find fascinating. I like the Ichthyosaurs mainly because that name translates to fish lizard, or roughly to fish lizard. And they may potentially, some of them, species, have been bigger than the blue whale, but it's all comparative anatomy, so it's a bit hard. So I find them. Or the, mental block. It's the giant placoderms, they're big fish from before life had kind of colonized the land that just had giant armored heads that were just like giant can openers. Had a bite of about a few thousand newtons, so not quite comparable to that of a great white or, say, a crocodile, but was still pretty strong. Like they may have been our ancestors, according to some more recent papers, but those things, I kind of want to see one, but I wouldn't want to see it while I was also in the water. They would have made going for a swim very, very difficult.
You want to see them in a tank?
As long as it wasn't glass that was protecting me from that tank, I still would probably... A giant armored head. Yeah. But that was kind of the early stage of the evolution of skeletons and bones.
Yeah.
It's just interesting to look at that. In terms of dinosaurs, my favorite living dinosaurs, so the birds, might have to go with the really intelligent ones like magpies and the crows, because they can recognize humans and you can form friendships with them. I've got one magpie that showing up. He'll even sit on my arm. I'm tempted to do a video on the backyard birds that I've got around my house. And I know it's he because you can tell the difference. The male magpies have a bit more white on the back of their neck. I know that's what most people probably weren't expecting when I talking about dinosaurs, to hear me talk about birds, but birds are dinosaurs. So yeah, Jurassic Park would look very different if it was with animals they actually could get hold of. But yeah, I don't think anyone would be scared of, like a kookaburra hopping around, biting people's ankles.
Although they can be vicious kookaburras.
Well,
sorry?
But then again,
they can be. But
they're sharp.
Yes, and one of them bit me the other day by accident. Thought my finger was food. But they're a little. They're not. I wouldn't say they're the smartest birds, but they're kind of cute. They're fluffy. Yeah. You want to hug them, but I wouldn't recommend it. They probably won't like being hugged.
No. You got to admit the cassowaries are pretty fascinating. Of all the extant dinosaurs, I'd say the cassowary is probably my favorite.
They're also terrifying.
I just have a thing for intelligent animals. But yeah, I've only ever seen, I think, one. That was a long time ago in a zoo.
Yeah.
I was in
These are
Papua New Guinea
interesting.
once, but I didn't get to see any cassowaries. They didn't come down to where we were very often. That would have been cool though.
I saw a cassowary in a zoo once, and I was like, I'm going to take 5 steps backwards. I know there's a fence between me and it, but Jesus Christ almighty.
They're big, well, they weigh more than an emu. And they're not as tall, but they are terrifying. And they, even though they're mostly solitary, they will hunt in packs. So it's like, yay!
Sorry, Brainbug put it in there. You reminded me, Dunkleostes. That's the big fish I'm thinking of. If you're going to go ocean. I'm a bit of an arachnophobe, so I won't go with the giant scorpions, the giant Eurypterids. But they're not probably my favorite. Wouldn't want to meet them either. Sorry?
You're going to disappoint Brainbug. He's an insect specialist. and I had to say that because I have forgotten what the name is. Mental.
I can at least remember that it's the Eurypterid.
No. Yeah. Okay, I'm going to shut up now because I've got a complete brain blank.
Now that you mentioned the cassowary, probably also adding to the list of birds that were probably terrifying to meet. I don't know. Have you ever seen the pictures or seen the skull? I think they've got a skull or a replica in the New South Wales Museum. I don't know how many places there are. Of the demon duck of doom, which is the kind of non-scientific name of it. Sorry?
What is the shoebill?
I think so. They're the giant, like, terror birds.
Are they like grey and you look into their eyes and you know that hell is a real thing?
Possibly, but we're now so they're the ones that like the Gastronus genus that you see in, if anyone's watched Walking with Beasts, the big terror bird that runs in and eats small horses and things. They do now, I think, based on isotope analysis, so checking the different ratios of the elements in there, that they were actually vegetarians. But they were these giant, like 2 meter plus birds. So like a massive cassowary with a beak that was about this big, with probably decent eyesight and a pretty strong bite force. They were not a bird you would have wanted to.
They had forward-facing eyes too, didn't they?
I think so.
Yeah, so that which actually wouldn't, which is probably the main reason why we thought they were predators to start off with, because that's generally a sign of being a predator.
Yeah, but maybe if they didn't have much prey, they wouldn't have evolutionary pressure to have them on the side of their head.
No, that's true.
I don't think a lot of things would want to hunt a big bird like that. I don't think it's
probably not. No,
who'd want to hunt Big Bird? Big Bird's adorable.
Yeah.
Sorry.
I have been getting a couple of questions in the chat about lightsabers. Is this another one of those I hate you movies situations? Like what? Like are lightsabers possible?
Not with light.
No.
Sorry.
No.
That's the problem with lasers and light, is that it tends to keep going till you stop it. And a lightsaber seems to go for about a meter or two, or about a meter and a bit, and then stop. I mean, that's not how light works. I've heard people try and claim it's more like a plasma thing, and then the light is like a byproduct, which I think is slightly more reliable. But also, if you look at laser cutters, they cut really close to the laser. They focus it down. So if it was a real laser, you'd have to probably hold it at someone's head for a couple of seconds for it to damage. Yeah. Again, yes, I know Star Wars has all the kind of crystals they use to power them, and maybe they have some weird power storage thing that we don't know of. It is, of course, science fantasy after all. But based on our technology, the ability to make a laser that's going to do significant damage, where the power pack fits pretty much into the palm of your hand, isn't. So yeah, the light in lightsaber is a bit of a misnomer if it was ever going to work. Also, laser beams don't travel in perfect parallel lines. They diverge. So after a certain distance, they will get wider. You can focus them with a lens and they'll get narrow, and then they'll get wider again. Yeah. So yeah, I don't see how they're possible. I'm great to watch movies with.
But even a plasma sword isn't really possible, not in the way Star Wars is, because whilst you can hold plasma within a magnetic field are not straight lines.
Yes,
so
that's the other thing.
You could have a laser bubble, a plasma bubble that you could use as a weapon, but not a laser sword.
Yeah, that's you're much better just firing a projectile at someone than that.
A plasma weapon
also,
would be possible. As in fire plasma as a projectile.
Yeah, I imagine that would do its damage. The other thing I've thought of, because in the Star Wars franchise, they're always shooting blasters that they kind of describe as like plasma bolts. And then the laser stopping that. And I've always thought, what would happen if you fired a real bullet? Because the real bullet, if it goes through the laser, when they show the lasers hitting metal, it melts it. So would it actually stop the solid metal bullet, or would it just melt the bullet and then the person gets hit by a molten lead, or a piece of molten lead?
Yeah, because
so
inertia would insist that it
fired a shotgun at a proper lightsaber. Sorry, this is probably a bit more into the inner workings of my brain.
Inertia would insist that the ball of molten metal would have to continue moving onwards, and we've seen,
or the laser would, so the lightsaber would.
Yeah, it should.
So
also,
either that or the lightsaber would get chucked
backwards.
Into your
Yeah,
face.
because if it's has enough force to actually stop it, then it's going to be pushed backwards. There's got to be recoil there. But it would. Which is what it would suggest would happen, considering they use lightsabers to cut through steel in Star Wars.
Yes. I've always, generally the people who make the movies are not scientists.
I mean, even in shows like Star Trek, where they actually usually had a physicist on set to help try to keep things somewhat sensible, you still you still let the narrative of the story run it rather than the science. There are very few science fiction shows that are actually heavy on the science. You occasionally get it in movies, more so than TV series, but it's I quite like The Expanse, because at least some of the concepts in The Expanse are closer to the real science than a lot of other shows are. But even The Expanse doesn't get it right.
I think Interstellar was one that actually listened to its science advisor until the end. And even how they depicted the black hole was based on the science literature of the time and what we thought it would look like.
Yeah.
The only problem I have is
papers
the very
were
ending.
written. The ending was bullshit, but weren't 2 papers written and actually published due to the studies done for that movie? Like
I believe so. Yeah, it was
like it was an actual genuine. It was a genuine. Like the movie directors actually put a lot of money into research and development for that. Which
I think the way they rendered it was exactly that. They put a lot of effort. So I will give that movie, except the ending. I won't actually say what happens, but anyone watch it, you get to the black hole, then just turn it off. That's my advice. Although I was watching it from a hospital, so not maybe there was other things going on. My own lab accident.
You need to talk about that one after.
Yes. I will. We would definitely get to that one. I don't know when you want to do that. Were there any other things you wanted to ask? Sorry, I know we haven't quite got to my area of research, because like usual, I am very good at waffling. Sorry, that's my bad.
No.
Get sidetracked easily.
This has been a great conversation. Okay, so we'll go to your area of research, how you have not become the next Spider-Man, and then we'll finish it up. So we have been going for about an hour. Don't forget
Bose-Einsteinian condensates.
And that one, and that too.
That one was a bit harder to do previous research in terms of how that works. Even I wouldn't pretend to fully understand that, because science is hard. But if we have time, I'm happy to get back.
Maybe
to that
we
one.
should. Maybe we could put that on with a different one, and maybe we could have both you and Dr. Carl on at the same time, and we could discuss both.
I would have no problem with that. I definitely would love to get on with Dr. Carl, or have a program, chat with him.
Yeah.
Okay. So I might as well just go on what my area of research is. To keep it really, really simple, we use lasers and sound waves to detect parts per million concentration of gases, greenhouse gases, for environmental monitoring. My PhD will be in building these. It's still relatively early terms, and COVID's kind of messed with schedules. So it's kind of early. I'm still learning about how to control equipment, do the electronics, but there's still a few papers out there. So for anyone who's interested, I'll pop the acronym in the chat if anyone wants to look it up. Sorry, let's see if I can spell properly. It's called KeyPass, and what it uses is a laser to make sound waves. Yeah. Probably thinking, how on earth does that work? So, as I mentioned earlier, you can methane has a particular absorption wavelength around 1550. Now, if you hit molecules with a wavelength of light that they will absorb, and that's all dependent on their electronic structure, that energy gets absorbed, and then they'll later relax, and they'll release another photon. But a little bit of that energy is lost to heat, because a bit of it goes into making the atom vibrate, and of course, if you increase vibrations, that's pretty much temperature. So if you hit the laser at the right wavelength, you can heat the gas. But if you take that wavelength of the laser, and you can do this with diode lasers, you can change their wavelength, and you start sweeping either side of it. You start heating them, then not heating them, then heating them, then not heating them. And you do that really, really fast. And if you heat something, just the way that gas laws work, if you have about the same container, or you heat something, you increase the pressure. That energy has to go somewhere, because now the atoms are moving, they want to push more on the outsides. So you can change the pressure with the laser. And if you get that to go up and down by changing the laser, as I said, you can get the pressure to change. And when you have a pressure change like that, that's sound wave. So you essentially use the laser to generate a sound wave of your preferred frequency. Now, I kind of say sound waves, they're well above what we would be able to hear, kind of in the kilohertz range, if anyone's interested. So most of them tend to do it at about 16,000 hertz. Pretty high. So you do need a lot of control over that laser. But what that does is you can now detect that with what is essentially a tuning fork made of quartz. So we're all familiar, or most of us should be familiar with how tuning forks work. We all know that if you whack them on the table or something, they'll make their sound wave, and you can get the different ones for whichever note you're after. But you can reverse that process. If you hit them with that sound wave, they'll start vibrating. So what we do is we use this sound wave that's coming off the gas that we're exciting with our laser to now move a small quartz tuning fork. And the benefit of quartz is that if you push on it, you can measure that electrically. Yeah. So all you do is you hook up a couple of electrodes to it, make a really fancy circuit that will make any second-year physicist or undergrad physicist cringe, because they don't want to look at capacitors and resistors and inductors again. I won't go into the details of the circuitry, but anyone who's gone through that trauma will know what I'm talking about. I'm a bit envious of the ability of electrical engineers. It's hard. But what you can do is you can measure this sound wave very accurately with the tuning fork. So the tuning fork is tiny. It's a couple of millimeters across. So it means you can make tiny, tiny little chambers, and you can detect very small concentrations of the gas. And if there's more gas, that pressure, the sound wave will be stronger. So you can think about it being a louder sound wave if there's more gas. And you can do that to figure out how much gas you've got. And if you can make them small, you can make them portable. The idea is, we kind of want to be able to get them onto drones and things. Because currently, when people talk about how much, say, methane is coming off a landfill, waste processing plant, etc., it's all a theoretical guess. So all this environmental monitoring, when they say this landfill will make this much greenhouse gases, is a guess based on theory. We don't have very accurate detectors, because the current ones, while the technology is getting better and we can get smaller, you still have to have someone go in there and put a detector there and run it. So we're trying to be able to do this more automatically. I won't go into too many of the details of exactly how, because early stages yet, but it's hopefully we'll be able to get a better idea of what we're doing to the environment with methane, which means better monitoring. We should be able to either utilize that better, and potentially we could use this to save lives. I've got a few ideas for industrial applications as well. So yeah, that's kind of the summary.
How do you know you're detecting methane? Like, is it because methane vibrates at when a certain wavelength hits it?
Yes, and that's exactly what we do. So we rely on each molecule, each element has very particular wavelengths of light that they will absorb. It's all to do with the electrons and how they sit. So even if I pull an electron off, that ion will be different from the previous element. And this is kind of
spectroscopy.
It does the electron shift between orbits. So when you raise as an electron absorbs energy, it will rise up in orbits. When it drops back down in orbit, it'll release a photon. So, but it's the same level of energy that requires it. You know this. You're a chemist.
I know this. I know this because
I'm teaching my grandmother to suck eggs.
I know. But
to Mark's comment, I will be able to tell if you do. And no, my father does not smell of elderberries. For fans out there. Okay,
your mother wasn't a hamster.
You actually did it.
No,
it's good that
at least I'm pretty sure. My mother definitely is not a hamster.
But Jen, no, it's really good that you explain that, because I know that, but that's high level chemistry and spectroscopy that you learn in university, and not every single person knows.
It's now in the high school syllabus.
Oh, it's in the high school.
So I do occasionally teach that through the uni. It's now new, but even the teachers have trouble with that. It's not an easy area.
Yeah, and it's not intuitive.
It gets more complicated when you're dealing with molecules, though, because now you've got lots of different interactions.
Yeah.
But you have to run a lot of tests to make sure you're not actually measuring other gases as well. So I've been reading the literature. Fortunately, though, methane, the gases that you would also generally get an overlap aren't going to appear in the atmosphere, or shouldn't. So you're generally all right. And you can control for most of it. But it's all stuff that has to be considered. So but thanks, Jen, for explaining that. Sorry. Yay, science is easy.
It's not. There's nothing easy in science.
It's cool.
It's fun, though. It is so cool. Yeah.
A lot of time.
Did you want to explain how you almost became a superhero?
I'm still waiting for my superpowers, but okay. So I got a couple of years, so it's about 4, maybe 5 years ago. So I just finished second year chemistry, and I was doing a summer project for a research group. I ended up getting my name on a paper for this, but the research project was in trying to develop chemical sensors to locate copper in brain cells to study things like, hopefully, Alzheimer's, dementia, Parkinson's. And so I made the control for it. But before I made the control, I was told to try and make a different chemical. And we were doing some reactions, and in chemistry, it's like Lego sets. If you want a big fancy chemical, you start with small building blocks, and you start attaching them together. One of those building blocks in the middle, one of the intermediates, turned out to be akin to a chemical weapon, and I accidentally spilt some of it onto my hand. Ooh. And washed my hand and felt no burning, nothing at the time. It was about midday when I did this, or no, probably morning a bit. And I didn't feel anything. I washed my hands. The PhD student with me said, you might want to make sure that it's clean. So I washed again. And then I went through the rest of the day. I finished the reaction, nothing. I was leaving in the afternoon, and I ran into one of my friends just on the main thoroughfare in the campus. And I noticed I was starting to fiddle with my hand. I was a little irritated. Like, that's interesting. I knew I was working with chemical irritants, so I didn't think much of it. And then I went rock climbing that evening, and my hand was starting to get a bit sore on the back of it. My palm was all right, so I could still grab things. By the time I got to bed, it was a bit puffy. It was swelling up, and I was like, this is slow. It's annoying. I have to keep an eye on this. And the next morning I woke up, and there's little blisters all over my hand. I was like, this is not good. So I couldn't drive by this point. So I was just like, Mummy. And my mum used to be a nurse, so she called up her friends in a hospital. They were like, okay, come in at this time. So we do. And by the time I got to ER, I had blisters on my hand that were like this big. It turns out I'd spilled what was essentially a sulfur mustard. So when you think of the mustard gases, this was a solid version of that. And over the next 4 days, it slowly melted the outside of my skin. I ended up needing a skin graft. I had that 6 days later, and that's where I saw Interstellar. I was sitting in the hospital after the skin graft, or that first evening, and it was like, I need something to distract from my hand. And I learned that I can't take endone because I start getting itchy. So that was fun. But yeah, this was skin grafts, and the chemical burns are not fun. Sometimes the burns will kill the nerves as well. This one didn't.
Thankfully.
And so I was in gloves and things. It was about 6 months. So that's my accident. This is not common, so I don't want to scare anyone away from chemistry. There is only one other person I've ever met who's ever had an accident with any similar chemicals, and his was nowhere near as bad. It was just one professor who had stories about everything.
Yeah.
like if you thought like he accidentally made cyanide in the lab once and had to evacuate everyone, things like that. I have not made cyanide, so I've never tried to poison myself that way. So I'm still waiting on my superpowers, because lab accidents is how you get them, but maybe one day. But that my hands are slightly different textures. I don't think it'll show up on the camera very well.
I can't see it.
But it's faded a bit. But yeah, if you have like a HD view of my hand, you can kind of see it.
The only lab accident of significance that I've undergone was I was playing with hydrochloric acid. Well, I wasn't playing with it, but I was wearing not the blue gloves. What are they? They're not,
the nitrile gloves.
The nitrile gloves. And nitrile gloves, when they get wet, they are really fucking slippery. There is like, I picked it up. I was holding it and it just fell and just landed all over my legs. So I just was like, oh shit. And then the lecturer was like, that's hydrochloric acid. That's a pH of 1. I'm like, oh fuck. Ran, stripped off. I just like, those showers are really, really cold. So here I was, I was standing butt naked, anyway, I had to throw out my jeans, and I was really upset. They were my favorite jeans.
Acid washed.
Yeah.
And I just got to add one thing into there in case some people don't know what we're talking about. When Meredith talks about showers, all the chem labs, because they deal with dangerous chemicals, have what are known as emergency showers. They are a giant shower head with like a lever with a handle, and you just, if something goes wrong, you run under them and you pull this handle and they dump a bucket load of water on you in a giant stream, and there are no drains either for them. They've got similar eye wash stations as well. Fortunately, I haven't had to use those. They're tested, but yeah, it's just straight out of the tap. So yeah, emergency. So not your typical like shower. These are in the middle of the lab. If something goes wrong, you yank it and get covered in freezing water. Sorry, yes. In case people
it's like standing under a waterfall. Like if you've ever gone swimming and under a waterfall, it's literally like that. Unfortunately, they have to be cold, is because heat speeds up chemical reactions.
And acids, when you dilute them, tend to warm up anyway, so you don't want to add extra heat.
Yeah.
You can actually get heat burns from acid spills on your skin as well, because people think, oh, let me wash it with water, and that process actually creates heat. So the best thing to do if you get something like sulfuric acid on you, if it's on clothes or you got those showers, it's okay. But if you don't, you wipe it off with like a paper towel first, then get the water. Otherwise, it could hurt even more. Fortunately, by the time I realized there was anything wrong with my hand, the chemical had already soaked through the skin. So it wasn't much I could do.
Okay, so we've got a few more questions and then we can probably wrap this up. So Nathan Jasper asks, do your lasers piss dogs off?
Okay, so I imagine that's to do with the sound frequencies. Unfortunately, no. For one reason, I work currently in the basement of the building because that's where they put the labs. So there aren't any
And
dogs
also-
nearby.
And also, they may as well like feed into this typical stereotype of the crazy science person in the lab in the basement going.
I haven't got an evil laugh.
Today? Take over the world.
But yeah, I think maybe I'm probably on some government watch list after talking about sharks and laser beams and the fact that I actually get to play with lasers. So. Yeah, so that's Dr. Evil to you, or almost Dr. Evil to you. There is that quote where he's like, when they call him Mr. Evil, he's like, I did not spend 6 years at evil school to be called a Mr. Yes, PhDs by the end of it do generally worldwide take about 10 years. So, like 10 years total. The actual PhD is shorter. Here it's about 4 years, 3.5, 4 years. So I'm in it for the long haul. And that's if I get through. Not everyone who starts will finish. So. If I don't finish it, I can probably still keep the name Almost a Doctor, because that's probably still correct. If we get it, maybe I'll have to, if the channel's still around and doing well by that point, I'll have to find a new name.
Yeah, well, I did notice that in chat. It's like, if you do get your doctorate, will you end up being almost a professor?
Depends what I do after that. Let's say, yeah. All right. So, questions, or you're going to say something?
Are there any more questions? I was just going to say, you could, if you do get your doctorate, you can say no longer almost a doctor. Or
yes.
Now a doctor.
Yeah, I don't know if it has the same ring to it, but I'll probably give the full story. If I get to 1,000 subscribers, I'll do a mini special and I'll give you the story as to exactly why. But yeah, roughly it is because I'm that. But there's a bit more to why I called it that. So I saw one question that was related to, what did that teach you about taking precautions in the lab? Sorry, I want to answer that one because I think it's actually it's a really good story. I've actually used this in job interviews because it did teach me a very good lesson. You can take all the precautions in the world to try and stop things going wrong. And you can minimize the danger. I'm all for that. But things will go wrong. I mean, 2020 has kind of showed us that that's almost an inevitability. And so it's very different to know what to do when things go wrong. And so it kind of taught me that I have to be prepared for things to go wrong as well as to try and prevent them. So you careful about wearing gloves, yes, but then you have to know what happens if I spill something on the gloves. Will the gloves stop every chemical? And it's kind of a different way of thinking about it. And so my kind of warning statement, this is not common. I'm the exception to the rule in that. So I have, yes, the lab accidents are not common, or they probably wouldn't let undergrads do what I was doing. And so, yeah, it's one thing to be aware of what you're doing, but another one to be aware of how you stop the problem. So, Meredith, you mentioned the shower, things like that. But that can go for your daily lives as well. You have to be prepared for when things go wrong. The original version of Murphy's Law is if there are multiple ways of doing something and one of those ways leads to failure, then eventually that will occur. I know it's not how most people normally think of Murphy's Law, but apparently, according to Dr. Carl, that is the original version. So,
if there's a chance of it going wrong at some point, it's going to go wrong.
And usually at the worst possible time.
Well, I mean, that's because whenever anything goes wrong, it is the worst possible time. But the fact that it's gone wrong.
Yeah.
Like, for example, for me, 2020, worst possible time. I have three 30 credit points left, one of which is 20 credit points. Supposed to be in a lab for both of my courses to finish my degree, course clubs, and then 2020 hit and the university shut down, and it's very hard to do a lab course when there's no lab.
I was trying to teach the first year ones last semester online,
no.
and that I could feel for you. But
but
labs online
No, like this is practical. Like I actually have to be in there to pass the course.
Are you going to go for your doctorate, Mary?
I want to go and get my master's first.
Your master's?
So,
yeah, well, obviously.
Yeah. But I might do. My main
Because that'd be cool
motivation
calling you
is-
Dr. Marrow.
It would be. The reason why I actually decided to start uni and go for my PhD was to show a friend, show that my friend that she's wrong.
Oh, okay. No, you haven't told me this story. Now you need to.
Okay. Well, I have a friend. She got very, very, very sick with a stomach infection. And she was on months and months of antibiotics. And I was telling her, you need to go and talk to a gastrologist to talk about your gut flora, because your gut flora is really, really important for your general health. And I was telling her all about the latest information regarding gut flora. And she's like, yeah, whatever, you're wrong, rah, rah, rah. And I'm like, okay, well, I was already going to go to university, but there is this little part of me that was like, you know what? I'm going to do my university. I'm going to get a PhD in fucking gut flora to show you were wrong.
That's commitment, Mara. That is commitment.
Yep.
that is how an Australian wins an argument.
I am going to get my PhD.
It'll only take me, 10 years from start of it. Well, maybe a bit shorter if you do.
Just don't you die
about
until I can prove I'm right.
But I will get there.
I will prove to you that I am right.
Yeah.
And then I was told her that 2 or 3 years later, I was part of the reason why I want to do my PhD was because of that. And she goes, "Yeah, no, you are right." I'm like, "God damn it, she's been a."
Oh, you could stop now, Mary.
Yes. I was looking at the comments. Yeah, that would be one way to win an argument. It's like,
It would be.
no, I actually have a doctorate in that area. I spent 4 years on it. Don't tell me I'm wrong.
To debunk
It's
your
the ultimate
thoughts.
argument from authority.
All right. Well, I think that's pretty much it. If anybody's got any other questions, I think everyone has actually. Mark, I have been able to access uni computers and resources, but the fact of the matter is, I actually genuinely have to be in the lab to do the course. I can't do it online. It's a skills development lab course.
It's even worse for you in chemical sciences because you cannot get most of those things to do it at home or anything. I mean,
I mean, you could, but then I think the government
you might get arrested.
Yeah.
I mean, I've got a similar problem to the laser experiment I want to do measuring the distance to the moon from the retroreflectors is going to require a laser of power enough that I should probably have a license for it. That's going to be awkward.
Yeah, I wouldn't trust you with it either.
I wouldn't trust me with a laser. Oh, damn it.
I'm surprised frankly, I'm surprised they let you use a toaster.
What can I do with this toaster? Give me a mic.
I mean, that's kind of the thoughts that go through my head on a daily basis. But I'm here and they've let me in.
Aunt Jo does actually good question. Has a question. Why are cats so obsessed with lasers? Does it have anything to do with their plan to take over the world?
Well, considering I had pet mice, I don't want cats taking over the world. This was ages ago that I had the pet mice, and I like my birds. So no. Maybe it's the plan of humans to stop cats taking over the world because we can distract them.
Yeah, that's true.
I don't actually know the biological reason. I think it's just shiny moving object. I mean, look. This is the weird thing that I find really interesting. We always get like the laser pointer. We're pointing at the cat, watching the cat go after the laser point. It's like, oh, look at this silly cat. And then, have you seen how excited we were today talking about lasers?
Yeah.
If you show a laser to me, I've got pretty much the same reaction as the cat.
Laser!
Where's the laser? Where's the laser? I mean, Jed's just described doing an experiment to bounce the laser off the moon.
Yeah.
It's like, yes, we're just like cats.
And we have to watch that
more
little
powerful
time.
laser.
Well, it won't be little. It'll be a couple of kilometers wide by the time the laser bounces back. But
Yes.
we are looking for that laser dot when it comes back. That's the whole point of the experiment.
And Omega Nuts, I'll make this one the last question before we wrap things up. Omega Nuts does make a good point and question, and it also leads into the Bose and Einstein
Condensates.
I can never
Kind
say
of.
that. How are lasers used to cool things down?
So it's actually quite complicated, and I'm not going to pretend to be an expert in quantum mechanics in terms of what's going on a tiny scale, but essentially we can think of heat, as I mentioned earlier, as kind of vibrations and moving. So if you have a particle that's vibrating more, it's going to have a higher temperature because temperature is a measure of energy, and that's kind of vibrations, rotations, etc. So with a laser, as I said earlier, you can trap particles. So if you can actually use that laser to hold that particle and stop it vibrating, exactly where you get that energy to go starts to get into quantum mechanics that I'm not going to pretend to fully understand. But you can actually hold those particles and stop them vibrating. If they do that, then you can actually get them to cool down. It was actually shown to me in a lecture, which shows exactly how much I remember from that lecture, but quantum mechanics was never my strong point, even though it's quite close to optics. In fact, there's a lot of quantum mechanics in optics, but it does have to do with not you don't think of the photon stealing the energy out as such, because you can't have that negative energy.
And you can't put more energy.
Yeah, so all the flat earthers who think the moon releases a cold light, that's not possible.
Yes.
But yeah.
Flat Earth theory.
I don't think we'll have it. Yeah. At least there's not many of them to upset.
That's true.
Yeah.
Maybe it's just that lasers are cool objects. Yes. I like Brain Bug's comment. Lasers are cool. Maybe that's just why.
If you're not, have you finished? Have you finished?
Yeah.
Go for it. Okay. So the reason why that really confuses me about Bose Einstein condensates, BECs, I'm just going to call it BECs, it's easier to say, is that so that if you've got an atom, let's say sodium, I can't remember what's sodium. What is that on the
Na?
I know it's Na. What is it number wise? What number is it? You've got the periodic table in front of you on your mug. On your mug, look at your mug.
From memory, yeah, 11. So I was going through the
11. Yeah, that's what I thought. That's what I was thinking, but I it's not my field. I was like, no, I'm going to be wrong.
So it's 11. So you've got all sodium atoms have 11 protons in it. BECs say that that you cool it down so much that a clump of sodium atoms actually starts behaving like a large sodium atom. And I'm just really confused. Is how can you have what's the difference between a BEC and 11 sodium atoms joined together as a molecule?
Okay, so there's actually different types, or at least you can observe BEC with different types of materials, different matter states. So when I was doing it for my lasers, we're doing it with what is known as a quasi-particle, which is when you get two particles and you energetically link them together. So it's almost not even a physical thing. Quantum mechanics is just weird. But the difference here comes down to one of the points in quantum mechanics, where it's the difference between, from my understanding, a fermion and a boson. Now, they're just ways of describing particles. So a particle can be either fermionic or bosonic. If it's electrons are fermions, and what it has to do is it tells you whether they can occupy what is known as the same quantum state. So when you think about how electrons can exist, we like to think about it as energy levels. We've mentioned that a few times today. You cannot have two electrons occupying the same state. You can have two on the same energy level because they have spin, so that way you've got different spins, so it's not technically the same. Whereas a boson doesn't need to do that. Bosons can all occupy the same state. I think neutrons are bosons from memory. Whereas fermions kind of have to fill from the ground up, and it's like filling a container. You fill the states up and up. So if you actually can get Bose, the boson, so the Bose is after, I know it's after the name, but it's to do with how it works. So with a Bose-Einstein condensate, they're acting like the latter. So they no longer need to have those separate quantum states. I hope this is the best area. Again, I'm not going to pretend to be an expert in quantum mechanics.
I'm not either.
Maybe I can on this too. It's probably a good idea for a video. Maybe how but that's probably how they can start behaving as one. The other thing too is that you can get them to all occupy the same state, the same ground state when you cool them, or the same excited state with very little energy. And that was how we were trying to get all of ours to work with lasing, where they all occupy essentially the excited state. So you don't need as much energy to do it as you would if they were all electrons. So this is getting quite complicated, but it's to do with that difference between the bosons and the fermions. They behave very differently, and for some reason, when you do get them to those temperatures, when you get the right conditions, they switch from one to the other. Like that, but we're talking about atoms as a whole. The electrons individually, yay, quantum mechanics, they're going to be weird.
Yeah.
Okay.
I don't know, does that help?
That does.
Yeah.
So thank you very much. That makes more sense. Okay, so let's wrap this up. So, Jen, I'll get you to tell us who you are, where you are, and all that sort of stuff. Chill yourself. Go for it.
I'm Jen from Jen's Little Corner. Go check me out on Twitter or YouTube as Jen's Little Corner. I believe Omega Nuts has been constantly, as he is the shill master, shilling us all out. So yeah, it's in the chat somewhere. It should also be in Mero's description. But yeah, I do science and LGBTQ content, and occasionally talk about sex, because sex is fun.
That is true.
And your comedy news, which
my comedy news thing, which somebody said, which is mostly the only thing I'm doing at the moment. But that's because of moving house. In the process of this, I'm not having as much time to edit and things, and doing live streams actually takes a little less time than actually editing and researching a video.
Yeah.
And Matthew, shill yourself, shill away.
So I'm almost Okay, so I'm almost a doctor, and that is my YouTube channel. I've recently started that. I talk about science and I try and pick interesting topics. So one of I think my last video was, do submarines fly? I've mentioned the nuke-powered space lasers, but if you want to find out the answer to whether submarines fly, it's actually not probably as silly as you're expecting. Then please head on over to my channel. I like to talk about science, and I'm hopefully going to keep doing this. It's a new channel, so I'm still learning, which means all my videos will hopefully keep getting better from here.
They definitely will.
Yes, while I have the opportunity, I want to thank both of you for having me on once again. I have
really
really enjoyed the chat.
No worries. This has been a really good one. I've really enjoyed this. My name is Meredith. My channel's name is Navadia. I'm sure most of you know that because you're here. But if you haven't, please don't forget, click the like button, the subscribe button, ring the bells for all three of us, yada, yada, yada. And also don't forget scandium, iodine, nitrogen, and cerium. Bye.